In this video, we're going to have a look at something called molecular ions. So we've come about these ever since GCSE. At GCSE, you probably had to learn the charges and formulae on some common ions that you could not predict from the periodic table, such as hydroxide, nitrate, carbonate, sulfate. That's pretty much it. Oh, and ammonium. So those ions you've not been asked really before A-level to draw dot and cross diagrams of. You've just been expected to memorise the formula, SO4 2-. And sometimes when people start trying to draw dot and cross diagrams for them, they get very confused because they're still thinking of an ion as basically only forming from an atom, such as say a chlorine atom with 7 in its outer shell, trying to gain 8 and gaining trying to get 8 and therefore gaining 1 electron. So if you only think of ions as loss and gain of electrons, you're going to get confused when it comes to these ions, because these ions formed from molecules. They formed from compounds that already contained covalent bonds. Now, your other part of GCSE told you that covalent bonding was also about filling up the outer shell. So it doesn't make sense to take something that already has a full outer shell and remove or add electrons. So where do molecular ions come from? They come from losing or gaining hydrogen ions. Hydrogen ions are quite special. They are just a single proton, because once you take the electron away and make H+, you're simply left with a proton with no electron shells whatsoever. Which means that it has its own chemistry. Acid-base chemistry is the chemistry of hydrogen ions being transferred, which means molecules often lose or gain hydrogen ions, and you do loads of examples of this in A-level chemistry. So let's look at how that applies to the dot and cross diagrams that we would draw for some common molecular ions that you have seen plenty of times before. Okay, so here's a couple of examples. When we're drawing hydroxide on the right-hand side, so OH-, we're not thinking of an oxygen atom bonded to a hydrogen atom which suddenly gains an electron. What we're actually thinking of is that we started with water and that the water loses H+ as it does because it naturally dissociates, as you will learn in your acid-base equilibria topic. So water, we're drawing it just as we normally would. It's H2O, single bonds to the hydrogens, but we know that water can split up. You also would have covered this if you did electrolysis at GCSE, that water contains hydrogen ions because it splits into hydrogen and hydroxide. So all I'm doing when I'm removing an H+ and losing or gaining a hydrogen ion, so that's what we're going to be looking at, is I'm literally just going to take away the H, because the hydrogen atom would be a hydrogen with one single electron. So the hydrogen ion would simply be basically like rubbing out the H in the diagram and leaving the electron behind. So that's how we remove H+, if you think about it. So I'm going to draw the first hydrogen, because water would never lose both of them. That would take too much energy to break both bonds. I'm going to leave both electrons behind, so you can see that I have a dot and a cross. The cross there was what belonged to the hydrogen, and the cross there is why the overall ion has a negative charge, because oxygen has 6 for its 6 electrons, the hydrogen has 1, and there is an extra electron. Other way round, ions like this can also form from gaining hydrogen. So ammonia has 3 single bonds to hydrogen and a lone pair on the nitrogen. Comes up a lot in shapes questions. Ammonia is a base, so ammonia will react with hydrogen ions and will form a dative covalent bond with that lone pair that's on top of the nitrogen, will bond with any hydrogen ions or remove them from water. And so all we've got to remember about both of these ions is because they are covalent and ionic, we need to draw the bonds, the lone pairs, everything else, but we also want to put the square brackets and put the charges outside the brackets. So that's 2 examples. What about one that's slightly more complicated? Well, we had a look at H2SO4 in the more complicated molecules that don't have 8 in the outer shell. So this is going to be a crowded dot and cross diagram, but it's possible. So that would be the formula of H2SO4. Oxygen's got 2 bonds, hydrogen's got 1, sulfur has got 6 with the maximum that it can have. And when H2SO4 goes into solution, as again you will learn in the acids topics, it dissociates fully into 2 hydrogen ions and the sulfate ion, which we know from having to learn at GCSE. Hence the 2 minus charge because it lost 2 hydrogen ions. To draw that as a dot and cross diagram, I'm first going to make sure that the bonds are all there. So double bonds are going to be dot, cross, single bonds, just a dot and a cross. It does not matter how many different atoms you have. You don't need to keep making up extra symbols for electrons. Okay, so it's enough just to say that one of those atoms is dots and one is crosses. There goes my oxygen. I'm now just filling in the lone pairs on the oxygen. There are no lone pairs on the sulfur because it's using all 6 of its electrons in bonding. I'm now putting my lone pairs on my oxygens, and then because they have single bonds, they have 1 electron left behind. If you count the dots around each oxygen, I've still got 6 dots. I haven't changed anything about the oxygen's electrons. I've just left behind an electron from each hydrogen atom. And just like before, we're going to do a square brackets and we're going to put a 2 minus around the outside. So there's a lot of electrons going on around the sulfur. There's 12 in total, but my oxygens have not disobeyed the octet rule because they're not in the right row of the periodic table, so 8 is their maximum, and therefore they're only forming 8 in their outer shell. 1 from the bond sharing with sulfur in the case of the ones at the bottom, and 1 from the bond that would have been with hydrogen that got left behind. So we've covered sulfate, hydroxide, and we've covered ammonium. We've not covered carbonate. Carbonate is very, very similar to sulfate, except for you just have the 1 double bond and 2 single bonds with the oxygen. So you can think of carbonate as coming from H2CO3, which is carbonic acid, basically. So all of these can come from dissociation of acids. We have not covered the nitrate ion. The nitrate ion is a little bit fiddly because it kind of has it has delocalized bonding. So we're unlikely to have to do that in a dot and cross diagram. That would be quite advanced, so we'll leave that one. But now you know how to do a molecular ion. The key thing is to think about the bonding first with the hydrogen attached or without, then lose or gain H+, and make sure that you either leave behind electrons if you remove H+, or that you're using a lone pair to bond with a hydrogen ion. If, like ammonium, you're gaining H+. And don't forget your square brackets with the charge outside the brackets every time.